In this video, we solved problem number 7 from written homework number 7 during the spring 2021 semester. This is just a homework problem that's featuring an integral differential equation along with an initial condition. We're asked to solve this equation subject to this initial condition using the Laplace transformation method. So we want to start in the same way that we always do. We let the Laplace transform of y of t equal big Y of s, or capital Y of s, just so that everybody knows what our notation represents. And then we take the Laplace transform of both sides of the integral differential equation. It just means it's an equation that contains the derivative of an unknown function y of t and an integral involving the unknown function y of t. So we have the Laplace transform of y prime equals the Laplace transform of 1 minus the Laplace transform of sine of t minus the Laplace transform of this integral because the Laplace transformation is a linear operator, so it's just going to, because of that property, the Laplace transform of the left-hand side is just this. We can factor out the constants and apply the Laplace transform to each of those explicit functions of t. This one, Laplace transform of y prime, is the Laplace transform of a function with a derivative, first derivative. So we would say n equals 1. In order to compute that transform, we need to use this. This is in our table. The nth derivative of f with respect to t has a Laplace transform with n plus 1 terms. We start with an s to the n times, the Laplace transform of little f, which is big F, minus s to the n minus 1 times little f at 0, minus s to the n minus 2 times little f prime at 0. And you continue until you end up with the n minus 1th derivative evaluated at 0. So let's look at this pattern. You're going to have n terms here, or excuse me, n plus 1 terms here. So see an R and then an M and then an S. Having a little trouble there. So you start with s to the n, and the rest of the terms start with a negative s to some power, and the powers of s decrease. So you'll have s to the 1 less power, and then the 1 less power, and so on until you have an s to the 0. So the last one doesn't have any s's in it. All of those are multiplied by, the first one is multiplied by f of s. That's the Laplace transform of little f. And then you are multiplying each of these guys by constants, and those constants come from the initial conditions. So this is little f evaluated at 0, and then the order of the derivative increases. So if this is the 5th derivative, this last one would be the 4th derivative evaluated at 0. And so we'd have f prime, f double prime, f triple prime, and then the 4th derivative, but all of those are evaluated at 0. And those are just numbers. We can plug those in because we'll have those in our initial condition. There are always n plus 1 terms for the nth derivatives Laplace transform. So if I've got n equals 1 here, I'll have n equals 2 terms. So I have s to the first times y of s minus s to the 0 times little y evaluated at 0. That's the Laplace transform of the left-hand side, and the right-hand side, it's actually relatively straightforward. The Laplace transform of 1 is 1 over s. Laplace transform of sine of kt is k, which in our case is 1, and I'm bringing that negative 1 down. So we'll have a 1 over s squared plus 1 squared, and of course 1 squared is 1. And this guy, involving an integral, has to be pattern matched to the convolution integral. So we want to think of this as the integral from 0 to t of f of tau times g of t minus tau d tau. That would make this the convolution of f with g, but we have to figure out what those two functions are. So over here, I'll have minus the Laplace transform of the convolution of one function with another function. I need to find the two functions. Now, the first function is the function of tau only. Well, in our case, we have y of tau. So if f of tau is y of tau, then f of t is just y of t. So that'll go right here. Now, there is no function of t minus tau, or there's no function listed explicitly. So that means that that function must be the implied 1. So if g of t minus tau is 1, that's just a constant function. If we shift tau units to the left or right on the t-axis, well, if it's a constant function, the y value is still 1. So this is the convolution of y with the function 1. Okay, so now we've got that there as the Laplace transform of a convolution. We still need to work that out. We know y of 0 equals 0 from our initial condition. And the next thing we need to apply here is the convolution theorem. The convolution theorem says that the Laplace transform of f times g, or the convolution of f with g, which we can think of as a special product, is the Laplace transform of the first function times the Laplace transform of the second function. So it's just f of s times g of s. Or in our case, it's going to be y of s times the Laplace transform of 1. So we've got s times y of s here equals 1 over s minus 1 over s squared plus 1 minus the Laplace transform of y times the Laplace transform of 1, applying that convolution theorem. Well, this is y of s by definition. That was our choice of notation. And the Laplace transform of 1 is 1 over s. So the equation simplifies to this. We have s times y of s equals 1 over s minus 1 over s squared plus 1 minus y of s, all divided by s. So we have taken the Laplace transform of both sides of the equation. Because it was an integral equation or an integral differential equation, we had to use the convolution pattern matching to figure out what that was the Laplace transform of. We knew it was a convolution. We wanted to know what was the convolution of. So we identified f and g, and then we used that Laplace, or the convolution property, the convolution theorem, which says that the Laplace transform of the convolution is this, to get here. Okay, and now you almost proceed exactly the same way that you would have with an IVP, with just a differential equation. You just want to get y by itself. So just solve for y, and then we'll take the inverse transform to figure out what y of t would have to be. We've got a y of s on this side and a y of s on this side, so I'll add this to both sides. And I think I'll factor out the y of s. So I'll have s plus 1 over s times y of s equals this 1 over s minus 1 over s squared plus 1. And here, in order to get y of s by itself, I could just divide by this, but then I'll have fractions in the numerator and fractions in the denominator, and it would be kind of messy. So rather than doing that, I recommend getting a common denominator here and then adding the fractions together. And then once you have a fraction times y of s, just multiply by the reciprocal to get y of s by itself. So I've got a 1 here in this denominator and s in that denominator. So the LCD is just going to be s. So I'll multiply this guy by s over s. That's just a well-chosen 1. Doesn't change the expression. It just changes the way we write it. And then we'll have an s in the denominator. So this will give me s squared over s plus 1 over s. Add the numerators. Keep the common denominator. That's multiplied by y over s. And that equals 1 over s minus 1 over s squared plus 1. Okay, now if we want to get y of s by itself and it's multiplied by this fraction, we can multiply both sides of the equation by that fraction. And that means multiplying each of the terms in the equation by that fraction, because multiplication distributes over addition or subtraction, right? So we can simplify from here. I've got an s squared plus 1 and an s squared plus 1. Those reduce. The s's reduce. So we just have y of s on this side. The s is reduced there. And the s does not reduce here. So I have y of s equals 1 over s squared plus 1 minus s over s squared plus 1 quantity squared. Okay, so that's what we had. Let me check my SIGN signs to make sure I didn't make any errors. That's negative, that's negative. We brought that over, that's gonna make that positive. Okay, that works, that works. I think all of my SIGN signs are correct. All right, so if I want to compute the inverse transform now to get y of t, that's usually the next thing we do. We would just take the inverse transform inverse Laplace transform of each of these pieces separately and then add them together, now this one is a basic rule. I recognize that. That's one that we see pretty often. The Laplace transform of sine of kt is k over s squared plus k squared. So the inverse Laplace transform of k over s squared plus k squared is sine of kt. If k squared is 1, that means k equals 1. So this is k over s squared plus k squared with k equals 1. So this guy is just going to be a sine of kt with k equals 1, or sine of 1t, which of course you could just call sine of t, and that would be fine. Okay, now this one with the s plus 1 squared doesn't look like any of the rules that we use often, but I recognize it as an s squared plus k squared quantity squared. So I'm wondering, is there an entry in my table that kind of looks like this? And if there is, let's use that in order to compute the inverse transform. So I'm looking for an s squared plus k squared quantity squared, and I have an s in the numerator. Now, if you see any k's in the numerator, don't worry about that because we can always adjust the constant. K is just a constant, but I need an s over s squared plus k squared quantity squared. I see it. Do you see it? There it is. 22. We've got a t times sine of kt, and this is 2 times k times s over s squared plus k squared quantity squared. Now the 2k is not there. Right now we only have a 1 in front of this s, but we could make that a 2k. We can always adjust the constant. So I know I need a 2k here. Let me write this rule down, and then we'll talk through the algebra that's necessary to make the form match. We want to make it match exactly. And the inverse transform of this is t times sine of kt. Okay, so k squared is 1. So clearly k equals positive square root. We're going to say 1. So I need a 2 in the numerator. I need a 2 times 1 up there. I can make that a 2 as long as I also divide by 2. So I'm multiplying by a well-chosen 1, a 2 over 2. Does not change the value of anything. But now I've got a rule for this, and there's just an extra 1/2 out front. So we'll bring the 1/2 out. You take the inverse transform of this piece, which is, according to this, t times sine of kt with k equals 1. So we'll have 1/2 times t times sine of 1t, which is just sine of t. So this is our y of t. If you want, you can factor out the sine of t. So you have 1 minus 1/2 t times sine of t. It's not necessary, but you can do it. And that is a solution of our integral differential equation. So let's go through the method again. It's actually pretty simple. You let Laplace transform of little y be big Y. You take the Laplace transform of both sides of the equation. And then for this piece, you have to think of it as a convolution. You have to say to yourself, okay, what's f and what's g? The function of tau is our f. So if we have y of tau and f of tau, y is playing the role of f. So you have y of t there. And g of t is the function of t minus tau, or g of t is implied by the function of t minus tau. But there is no function of t minus tau listed explicitly. So that means that g of t minus tau is just 1, which looks like this. It's just a constant function, y equals 1. If I'm subtracting tau from t, that means I'm shifting the graph of g of t tau units to the right. Well, if I shift it back, tau units to the left, and my function is a constant 1, then it's still 1. It doesn't change anything because there's no t explicitly on the right-hand side. The equation is, or the function, excuse me, is just a constant function. So this is the Laplace transform of y times 1, or the Laplace transform of the convolution of y with 1. And then according to our convolution theorem, that's the Laplace transform of y times the Laplace transform of 1. After substituting in our initial conditions, you just end up in pretty much the same place you would with any other IVP. You've got y's on both sides, you want to get y by itself. So we add this to the other side. We have this, we can divide by this to get y by itself. To simplify our lives, we will get a common denominator over here, which is this, which gives us this. And then once I've got a fraction times y equals this, it's easy enough to get y by itself by just multiplying everything by the reciprocal of this guy. And when we did, we got to this point, and we said we have a rule for that. We said, I don't know the rule for that off the top of my head, but it looks like one of the rules in the table, so let me look it up in the table. And sure enough, there was a rule in the table that worked. So we had to recognize this rule in the table and then say, I don't have a 2k. Remember, the k is just a constant. You can always multiply, you can always adjust the constant. And then k is equal to 1 because of this s squared plus 1 squared. The k squared is 1, so k is equal to 1. So I knew I needed a 2 in the numerator to match this form. So I just made it a 2, and that was totally legal as long as I compensated by dividing by 2. So I multiplied by 2 and I divided by 2. It's like multiplying by 2 over 2. It's like multiplying by 1. So then I brought my 1/2 out, which is a constant. I took the inverse transform of that, and I got that, which gives me this y of t. So you just take the Laplace transform of the equation, you solve for y of s, you take the inverse transform to get y of t back. Now, if I take this function and I evaluate it at t equals 0, clearly y of 0 equals 0. Good, y of 0 is supposed to be 0. If I take that function and I differentiate it and I evaluate this integral of y of tau from tau equals 0 to tau equals t and subtract, if I evaluate all of that and then I simplify the left-hand side and the right-hand side, they're going to be the same. So that means y of t is a solution of this integral differential equation subject to this initial condition.